So this is part two. For the image graphs, we're going to go over the remaining parts of the checklist for the image graphs. In this case, we're going to start off like I try to tell you guys when you're presenting, just add a slide to give us some context. And so in this case, we're going to be graphing the viaduct. In my last video, I didn't do a translation down, so we'll go over this right here. So you can see the scale of this viaduct. And as we go through, we'll see a couple images that try to give you the setting of the place that we're graphing. So this town in France, Morlaix, France, in the region of Brittany. And I just give it from a few angles. Like I said, it's not that much work to really lay the setting. And then we're going to see a graph. In this case, we have a label of the location. We have clearly labeled which one is the pre-image. The pre-image in this case is f of x equals x minus 0 squared. And so that would be the x-coordinate of the vertex. And because that's a 0, we can see that the vertex is directly on the x-axis. And then the y-coordinate of the vertex is positive 6.2. So we can see that it has a border in orange, so we can tell which one this label corresponds to. And then we can see that this was a translation down by 4.8 units because this y-coordinate is 6.2 and this y-coordinate is 1.4. So if you add 4.8 or if you subtract 4.8 from 6.2, we would get 1.4. So we're clearly labeling what a translation down would look like. And then I give a little fact about it so that you can understand the scale. So that would be maybe something that a slide that would get a 5 out of 5 would be. Something that would be clearly labeled, and that when we print it out and put this on the wall, it would give us a little bit of a fact and explain the scale. But you can see this is a very large structure. So that's why I included that fact. It's also somewhat modern compared to the medieval village that it's kind of set in. You know, this village is pretty old, much older than this structure. But, you know, obviously it's been around for almost 200 years. So still we can see that it's younger than the surrounding village. So give us whatever facts you can. You don't have to go into too much detail, but some kind of context would be helpful. Next, we're going to take a look at another medieval type village. You can see these structures, these buildings are, from a different era of architecture, and they're still standing. You can see some of the stones, the streets, the way that they're laid out. And, obviously there's cars to show, what it looks like in the modern day. But, we could imagine that this would have looked pretty similar hundreds of years ago. So interesting form of showing like the village, the setting that I'm trying to show you guys around, so you guys want to try to do the same thing. And in this case, the next graph is going to talk about this cathedral that's set in this village, and so you can see it in the background, and it's one of the biggest structures in the village. And then from this side, we can see that comparing it to every other building, we can see that it's much bigger and it kind of dominates. From the aerial view, it's easier to tell, but you can see that it's probably going to always be in the background. So again, this is in the village of Dol de Bretagne. And so now when we go inside this cathedral, St. Samson Cathedral, there will be a label of that. And you can see that this time I wanted to do a vertical compression by a factor of 0.13. So to do my vertical compression, I wanted to show a narrow parabola that would be getting wider, and that was the idea of a vertical compression. So we can see that in this case, the pre-image is represented in green, and the transformation of this, the only difference between these equations, they have the vertex at the same location. So notice that's one requirement of getting the vertical compression. You need two parabolas that would have the same vertex, and you want to have the second one be wider than the first one. So in this case, I think we've clearly shown the difference between these two. You can see that the vertices are the same. We have +3 and +3. The number inside the parentheses that gives us the x-coordinate is 0, so the vertex is right there on the y-axis. And we can see the only difference is the leading coefficient. In this case is 0.13. And so that's why we have a vertical compression of 0.13. So this would be one way. In this case, I don't have a fact about the cathedral, but like I said, that might be some way that you guys could collaborate with your partner so that you end up with a presentation where everything's a 5 out of 5. So try to do a little bit of research and make sure you understand that, you know, if you have two partners in your group, that each one of you needs to create a vertical compression. So don't count on just one of them. Okay, this one, what you're looking for as you search through images, like I said, you're trying to find two parabolas that have the same vertex. So you'll kind of know it when you see it, and you'll have to be looking specifically for that one. If you find images that you feel like would be suitable for another one, then go ahead and save them, open them in a new tab or something. But in this case, you know, the model's pretty decent. You can see that the red parabola starts to not fit this arch at a certain point. So, you know, I adjusted my coefficient until I found that if I changed it anymore, I would get a worse fit, so that the parabola would be open too wide or it would be too narrow. So in this case, I got a pretty good fit in between these two intercepts that we have right here. And after that, it starts to kind of go away. So the green one also has a pretty good fit too for the parabola. It doesn't fit so well at the beginning at this point because it kind of comes to a point. It's not so smooth at that part, but overall it's a pretty decent fit. It's not a perfect fit, but it's a good fit, so it, you know, partially models it. So now I'm moving on to the higher degree polynomials. This one is an architectural model of a proposed college in the city of Nantes, France. And I thought this was a great example. There's a curve in the background that fits a fourth degree polynomial pretty well. I think I accidentally labeled that as a 6th degree polynomial, so I would go change that to say 4th degree polynomial. And then I might need to lower my font size a little bit so that this all fits inside. So as you can see, we have a 4th degree polynomial. It's a higher degree polynomial, and it fits. This might be something that I could try to use a complex pattern. In a second, I'll give you guys some of the rules of a complex pattern. But you know, I see a lot of arches. At once I tried to graph this thing to see if this was a parabola, but it wasn't really parabolic. And then I realized that up here, this picture would be better served as the higher degree polynomial because it fits this curve very well. So sometimes you'll get lucky. If you're having trouble with the higher degree polynomial, just recognize that the 4th degree polynomials are a little more flat. You can use the same vertex form. If you change that to a 4, then in this case, you'll basically have the same idea, right? This vertex is at negative 0.32 and the x coordinate is 0. And if you change the leading coefficient, you'll be able to get something that hopefully fits the shape that you're looking for. Again, the 4th degrees are a little more flat, and so that might help you if you find a curve that fits that. And then I came up with another idea for this fence. When I saw this fence, I tried a little bit to get it to fit, and because I wanted to get this video up, you know, I stopped working on this specific graph because I wanted to give you a few examples. But in this case, what I did was I recognized that if I lined up this image with the x-axis and made it so that this intercept with the x-axis was at -8, then I would have a factor of x plus 8. And then likewise over here, we have a factor of x plus 3 because it crosses at about -3. So you can see that point right here. So that's where those two go. And then what I had to do was imagine, you know, how it would turn back around. And so I would keep playing with these numbers because it's not totally perfect, and I could try to get a better fit. But again, I added in a -5 so that I could start to have the function bend back around. And so this is not quadratic. This is a 3rd degree polynomial because we have 3 factors and we have 3 x-intercepts. So in this case, you can see that we have x minus 5 and it crosses at +5. Again, don't forget that your intercepts will always have the opposite sign of what's in the binomial with the factor. So after I got those zeros, the graph was not totally lining up. And so then I started to change the leading coefficient in order to make that fit. So again, these ones are like more of a challenge and you have to be creative. So one way to do that would be to try to line up the zeros and make that fit to get this one. Then we want to discuss the comparison with the circular equation. So we had an assignment on Desmos where I taught you guys how to use this notation in Desmos in order to get only partial equations graph so that we didn't have the whole graph. So in this case, it's only giving me the values of the graph that have a y coordinate that is greater than 1.5. And we could see that this circle is in the black dotted line. And so this line, this dashed line, represents the arch almost perfectly. And the blue parabola, the parabolic function, I didn't type it in here, but this would be where you type it in. And in this case, you would show, with some kind of distinction, you'd make a sentence or some kind of label that would help us actually make the comparison, right? So we put both of them on the same slide and we try to see which one fits better. You might find some arches that are closer to a parabola and you might find some that are closer to a circle. There's many different kinds of arches. Some of this Gothic architecture that we're looking at, maybe neither of them is perfect, neither is circle or a parabola. And so you just try to say which one you think would be the better model. So, try to find a circular arch. I think that would be an easy way to do it. A lot of archways, walkways will be semicircles. So if you could use that notation that we use in Desmos to kind of cut off the section where it stops working, I could do the same thing for my parabolic function and show that, the parabola only really models the circle, this circular arch well in between these 2 points, whereas the circular equation models it perfectly in between these 2 points. So in this case, I have a label that says the circular equation is a better model for this arch. One thing that I suppose I forgot to put here would be a label of this location. So in this case, this isn't in Brittany. This location right here was from our project in Granada. And so I was just trying to refer you guys back so that you would remember this assignment and that you've done this kind of work before. So there is a video on graphing circles. If you're confused about how to do that, you could watch that video and hopefully that'll go into more detail about how to do the comparison with the circular equation. And you would want to have both the parabola and the circle on the same slide. So it shouldn't be too hard. A lot of arches are already circular, so just do your best. But if the parabola fits it better, then that would also be something you could say. You could say the parabolic equation is a better model for this arch. So now we have the rules for the complex pattern, and this is what you guys should follow. A complex pattern must show 4 or more intersecting parabolas that create a pattern, or the complex pattern must show 6 or more non-intersecting parabolas that create a pattern. So if you want to do your work with less equations, then you'll have to be creative and see that the pattern is there. And if you can't really find anything and you want to get a pattern that's up so that your slide exists, then what I would say that you should try is put 6 or more non-intersecting parabolas to try to get a 5 out of 5. We really want a clear pattern that is visible, that we can notice by looking at your equations and kind of being able to see what was adjusted. So we'll talk about what that might be. So let's talk about this first one. We have 4 intersecting parabolas. In this case, we have this ceiling detail that I've shown you guys before, and we can see that using these 4 parabolic equations, I did these f of x equations, and those are concave up and concave down, whereas the left and right equations are these f of y equations. And so if you would like to do a left-right parabola, if that ever becomes necessary, then that would be a good question to ask me. Send me an email about that. But in this case, this would be one idea, right? We have four parabolas and they intersect and they create this almost floral pattern that we have here. And we can at least notice that it almost matches up with the shapes that we have here. So it's some way that we can model a pattern, and you guys can also learn how to kind of use parabolas as a design tool. All right, so I would say spend more time working on the other slides. The complex pattern is kind of the icing on the cake here. So, you know, keep looking around. Hopefully you'll know it when you see it. But again, this would only take four parabolas because they do intersect. And if you wanted to find a pattern where they don't intersect, then what you might want to do is take a look through. Let me try to give you an example. When we look at this cathedral, say this one that I used to show you guys a reflection across the y-axis, and I know this image is kind of pixelated, so if I wasn't trying to get this video up quickly, I would do this slide again, but I'm going to go ahead and post this. You guys can hopefully see how there's a lot of almost parabolic arches here. Maybe we could see one arch, 2, 3, 4, 5, 6, right? And they're all kind of parallel to each other because they'll never cross. So you might be able to give me 6 different equations to get all the different parts of this arch, all these little details, and maybe 6 different equations would show us, you know, each different section. So you could try to figure out a way to lay that out. You could be creative with that. I guess you could do them all in the same color, but maybe just try to write them in a vertical order. Or maybe you could find another more complicated pattern, maybe with you know, 3 arches next to each other and then 3 above of each other, and just try to show how it would work. So this is just one idea. Like I'm saying, if they don't intersect to create a pattern, then what you would want to do is find 6 of them to where you can show a pattern that exists. So just be creative. You know, in this case, you can see that there's a few parabolic arches that we might be able to graph. And so in this case, you would just do whatever you could to try to find 6 or more that you could put on the same image. But you really want, in the spirit of this one, to find a pattern that would be able to emerge. So it might not be so simple, and that's why it's called a complex pattern. But like I said, you know, if you should be able to recognize it when you see it, once you're looking for it. So make sure everything else is done before you get that. I'm going to go post this video now, but I hope you guys can see that this example, in this case, this is more semicircular than parabolic. So this would also be a great example of, you know, a circular equation I could use to show this arch, and that the parabola only partially does one section of the arch, whereas a circle would do a more complete model of this arch. So I hope this explains how we could check off different values from our checklist. So in this video, we've seen how to check off the translation down, how to check off the vertical compression, a third degree or higher polynomial, a comparison with a circular equation, and a complex pattern. Okay, what I might do right now is just show you really quickly how I got the third degree or higher polynomial, because there was a third degree model. And so I will go to Desmos and open up that file so that we can take a look at it. So don't forget to save your work. It could be helpful. And in this case, I'm going to go to the house that I made. And as we look at this specific function, we can see that it has the intercepts that we need. And notice that right now it doesn't fit at all, right? There's nothing else here other than these 3 parentheses, because I knew I wanted the graph to cross here and here. So one thing that I had to do was move my image around until that fence crossed the x-axis at some integer points, just to make the calculation simpler. Then what I did was I went to the leading coefficient and I started putting different numbers in there. If I was to put 0.9, 0.8, 0.7, 0.6, 0.5, as I change these numbers, you can see that the graph isn't getting much more narrow, but you can see that these critical points are coming down a little bit. So it's getting a little more flat, right? And I want this to line up with this part. So I see that I ran out of numbers, it would appear, but you got to remember there's lots of numbers, right? And so this looks like 10 cents, right? So think what's less than 10 cents would be 9 cents. So we could change that to 0.9 and 0.8, 0.7, 0.4, 0.3, 0.2, 0.1. And you can see once I change that to 0.1, the graph starts to coincide a lot better. So this model is decent. And in that case, this is a third degree polynomial that is lined up. Okay. This x minus 5, how that came about was because I wanted to get this to fit. And so if I was to change that to x minus 2, you can see that this part is kind of bending this branch of the function in between here, right? This little section of the function in between -3 to -2. So if I change that to 3, we can see that the function starts to kind of bend so that it coincides. And if I go too far out, it's going to drop below where I want it to be. So I felt like 5 was a good point, and everything else kind of stays the same. So that's what you would do, is if you need a higher degree polynomial, if you want it to be an odd function, you could just go ahead and line up whatever it is you're trying to model, line up the graph so that it crosses, line up your image, right? Move it so that your graph of your x-axis, the x-axis crosses this thing you're trying to model at an integer point. And if you can't have it cross at an integer point, then you could just deal with the coordinates that you have there. So if you're ever worried and you can't figure out how to find the coordinates of a point, then what you could do is just make a point, 0, 0. And then if you do a hold click, if you just left click on this thing right here, just click down and hold it, you can click drag, this little option right here. And then what that does is it'll create a point with whatever color you have. In this case, it's red. So if I change the point to green or whatever color I would like, orange, in this case, green will stand out a little more. Then what that does is it will let you drag the point around, and you can start to see the coordinates change. For instance, it tells me that this point right here is -3, 0, and it tells me this point is -8, 0. So that can help you if you're having trouble seeing exactly what point you're looking for. Just create a point. Just put parentheses, put 0, 0, and then in order to drag it again, just left click there and make sure that you check this option. If you don't have that option checked, it's not going to let you move the point around, right? So just check that box, and that will let you move the point wherever you want to put it. And then you can kind of inspect something. If I wanted to see like where this point was, you can see that the x coordinate is at -5.4 and the y coordinate is at 0.67. So I hope this is helpful. You guys can see how many tabs I have open right now, and this is basically comes along with the idea that, you know, do your research one step at a time. Don't go back and forth so much, right? Find a lot of images, open them up in new tabs, and then from there figure out which one you're going to be able to actually use, right? So I hope you guys have some luck finding your images. I try to give you advice in how to do the third degree or higher polynomial right now. The complex pattern is going to take a little bit of extra work and creativity to find. But again, don't forget the rules that I gave you here, is that the complex pattern must show 4 or more intersecting parabolas that create a pattern, or if they do not intersect, then I would like 6 or more parabolas on the same slide, and you just try to illustrate what the pattern is. I've had some students asking me how many slides are necessary, and I hope you guys realize that the most important thing isn't necessarily the number of slides, but that you check off all of these 14 boxes here. So you might be able to do 3 of them in one slide, as in the case of this bridge. Okay, again, what's missing here is a label of the name of this bridge. And so I have a little more work to do on the sample presentation, but you can see how factored form, vertex form, standard form, these are all different forms of the same exact parabola. And so I was able to check off 3 of those boxes with one slide. So I hope you guys, you know, realize that you can do this many different ways. If you want to have 3 different slides for factored form, vertex form, and standard form, that's fine, but you don't have to. So do the best you can here. You should be able to wrap up your project now, at least with the idea of your image graphs and your population model. This would be a great start. If you have all that done, you're doing great, and I would consider yourself not behind once you have all of these things checked off, right? So if you don't have them all checked off, then make sure that you realize final week is coming up and you guys got more work to do. Don't forget the idea of having just one slide ahead of time to try to set the context of the thing you're graphing. And when I print these out, it would be nice, I might put them together where we have like a context slide and then a label slide, right? So if I was going to print out this graph, I would probably also print out this picture to put on top of it so that we can kind of see what we're looking at. Okay, so good luck. I hope you guys don't have too many problems trying to find images, but again, your models don't have to be perfect. Like in this image right here, we can see that the parabola doesn't fit perfectly, but it models part of it, and so that's part of what we're trying to learn here, is that not all arches are parabolic. Just because it looks like it might be parabolic doesn't mean that it is. So please let me know if you have any questions and get your project done. Good luck, everybody.